This week, we're not just tracking progress. We're witnessing a quiet revolution in how AI sees, speaks, thinks, and creates. 5 breakthrough papers. One theme, rethinking the foundations of machine intelligence, not with incremental tweaks, but with fundamental shifts in representation, learning, and efficiency. From infinite depth maps to on-device video generation, from speaker-aware transcription to alignment that actually works. This is AI evolving beyond the limits of its own architecture. Let's dive into the 5 advances that are already reshaping the frontier. #1. InfiniDepth, the end of grid-based depth estimation. For decades, depth estimation in computer vision has been trapped by a single constraint, the pixel grid. You feed in a 1080p image, and the model outputs a depth map, also 1080p. Want higher resolution? Upsample. But that's just interpolation. You lose edges. You blur fine details. You get holes in your 3D reconstruction. This isn't a bug, it's a feature of the paradigm. The model assumes depth is discrete, tied to pixels. But in reality, the world is continuous. Enter InfiniDepth, a radical departure. Instead of predicting depth on a fixed grid, InfiniDepth treats depth as a neural implicit field, a continuous function that maps any x, y coordinate in the image plane, even subpixel locations, to a depth value. How? It starts with DINOV3, a vision transformer that extracts rich, multi-scale features across the image. These are fused with a multi-scale local implicit decoder, a lightweight network that learns to reconstruct depth at arbitrary resolutions by blending high-frequency details with global semantic context. The result? A depth map that's resolution agnostic. You can generate a 4K depth map from a 1080p input, without upsampling, without blurring, without losing a single edge. But the real innovation is infinite depth query, a solution to a long-standing problem in novel view synthesis, density imbalance. When you render a scene from a new viewpoint, points near the camera are densely sampled, while distant objects are sparse. This leads to holes, distortions, and artifacts. InfiniDepth fixes this with a geometric weighting function. WXY proportional to D2NV. This weight reflects how much surface area each pixel projects into 3D space. High weight right arrow, more query points. Low weight right arrow, fewer. The result? A uniformly distributed point cloud, even under extreme viewpoint changes. They tested it on Synth 4K, a new 4K synthetic benchmark built from AAA game engines like Cyberpunk 2077 and Spider-Man 2. It includes high-frequency textures and complex geometry to stress-test fine details. InfiniDepth outperformed Mode G2, Depth Anything V2, and Marigold, especially in high-frequency regions, where it led by over 10 percentage points. And when paired with Gaussian splatting, the 3D reconstructions are cleaner, denser, and visually superior, with fewer holes and sharper geometry. This isn't an upgrade. It's a new representation, where depth isn't a grid but a function of space itself. InfiniDepth, arbitrary resolution and fine-grained depth estimation with neural implicit fields, a true leap in how AI perceives the 3D world. #2. EAFT, fixing the catastrophic forgetfulness of fine-tuning. Fine-tuning is how we specialize large language models. Teach them math, medicine, code. But here's the paradox. The more we fine-tune, the more they forget. This is catastrophic forgetting, a well-documented failure mode. But the real culprit isn't the process. It's the data. In supervised fine-tuning, SFT, models are forced to align with labels, even when those labels contradict what the model knows. And the worst kind of conflict. Confident conflicts, when the model is highly certain about a wrong answer. Imagine training a model to believe a ball is a truncated icosahedron, not because it's confused, but because it's overconfident. The loss function sees this as a massive error and applies destructive gradients, rewriting the model's internal knowledge. But here's the twist. When you use on-policy reinforcement learning, this doesn't happen. Why? Because RL data is either high-confidence correct responses or high-uncertainty exploratory ones. No stubborn misalignments. So what if we could simulate that behavior in SFT? Enter entropy-adaptive fine-tuning, EAFT, a simple, elegant fix. EAFT uses token-level entropy as a gating mechanism. At each token, it computes entropy over the top 20 predicted tokens, which capture 99.9% of the probability mass. High entropy, the model is uncertain, learn freely. A low entropy, the model is confident, but if the label contradicts it, downweight the loss. No data filtering. No complex rollouts. Just a small change to the loss function. Loss equals 1 HT times LT, where HT is entropy, and LT is the standard cross-entropy loss. The results? A Pareto improvement. On math AIM, GSM 8K, medical QA, MedMCQA, and tool use, EAFT matches or slightly exceeds SFT. But on general benchmarks like MMLU and IFEVAL, it preserves performance, while SFT drops by 10+ points. And the gradients tell the story. In SFT, confident conflicts light up in dark purple, massive, destructive updates. In EAFT, they fade to pale. The model isn't being forced to rewrite its priors. This isn't a trick. It's a mechanistic fix, one that respects the model's internal state, not just the label. EAFT isn't just better fine-tuning. It's continual learning made practical, where you adapt without erasing. #3. MOS Transcribe Diarize, the end of speaker chaos. Imagine a transcript that knows who said what, when, and how, with millisecond precision, no errors, no fragmentation. Most systems are modular, ASR first, then diarization, then stitching. But errors cascade. Speaker identities drift. Long-range references break. And most can't handle recordings longer than 90 seconds. Enter MOS Transcribe Diarize, a unified multimodal LLM that performs speaker-attributed, time-stamped transcription in a single forward pass. No handoffs. No chunking. No boundary artifacts. Here's how it works. 1. End-to-end design. The model jointly learns transcription, speaker attribution, and timestamping. No pipeline, no error propagation. 2. 128K token context. It can process up to 90 minutes of audio in one go, no truncation, no stitching. 3. Explicit time encoding. Instead of fragile positional encodings, it inserts formatted timestamps directly into the input stream. Good morning. Morning, guys. Hi, everyone. This allows the model to learn precise temporal relationships, even across hour-long recordings. Training. A blend of real data, AISHELL4, and synthetic conversations generated by a probabilistic simulator that adds realistic overlaps, noise, reverberation, and Gaussian turn gaps. The results? Stunning. On AISHELL4, 15.43% CER, better than GPT-4o, Gemini 2.5 Pro, and Dubbo. But the real win? Delta equals 4.61%, the lowest across all systems. That means speaker attribution errors contribute less to overall degradation. On podcasts, delta of 2.5%, even when speakers return after long pauses, MOS remembers. On movies, it handles dense overlaps with precision, while others fail. And unlike GPT-4o and Gemini 3 Pro, MOS doesn't truncate long audio. It just works. This isn't just better transcription. It's intelligent conversation understanding for legal depositions, meeting assistance, podcast analytics, and assistive tech. MOS Transcribe Diarize is the new gold standard, and it's already live. Try it at MOS Transcribe Diarize Demo, MOSI, CN. #4. GDPO, the fix for multi-reward reinforcement learning. Alignment is how we teach models to be safe, concise, coherent, efficient. Most use GRPO, Group Relative Policy Optimization, a popular RL algorithm. But here's the flaw. GRPO collapses reward signals in multi-objective settings. Consider two responses. 0-2, correct but long. 0-1, correct but shorter. GRPO normalizes both rewards together, giving them identical normalized advantages. -0, 707, 0.707. But that's wrong. The first should be rewarded more for being correct. This reward signal collapse leads to poor convergence, even training failure, especially in math and coding, where objectives compete. Enter GDPO, Group Reward-Decoupled Normalization Policy Optimization. GDPO normalizes each reward independently before summing. So, 2 right arrow -1, 414, 1.414. 1 right arrow -0, 707, 0.707. The distinction is preserved. Then batchwise normalization stabilizes the scale. The result? A richer, more expressive training signal. Tested on tool calling, math reasoning, and coding, GDPO consistently outperforms GRPO. Tool calling, up to 5% higher accuracy, 4% better format compliance. Math AIME, 6.3% higher accuracy, length violations dropped from 85% to 0.2%. Coding, higher pass rates, fewer bugs, shorter responses. And here's a deeper insight. Reward weights alone aren't enough. If one objective is easier, the model will exploit it. So we add conditioning. Only give a length reward if the answer is correct. This forces the model to prioritize hard goals first. Combined with GDPO, fine-grained, predictable control over alignment. GRPO was never built for multi-reward settings. GDPO fixes that. If you're aligning models with multiple preferences, safety, structure, efficiency, stop using GRPO. Use GDPO. #5. Rehi-at, on-device long-form video generation. Video generation has been stuck. We can generate 10-second clips from text, but 1-minute scenes. 5-minute reels. The bottleneck. Self-attention, which scales quadratically with sequence length. A 5-second video at 480 times 832. Tens of thousands of tokens. Multiply by layers. OOM errors. Even with flash attention, it's impossible on standard hardware. Linear attention fixes scalability, ON instead of ON2, but sacrifices quality, blurry motion, flickering, inconsistent identity. Hybrid models. Often still quadratic. Enter Rehi-at, recurrent hybrid attention, a breakthrough from Qualcomm AI research. Rehi-at splits video into temporal chunks, say 3 frames. Within each chunk, it uses softmax attention for high-fidelity local motion. Between chunks, linear attention handles long-range coherence. But here's the genius, it's recurrent. Causality is enforced, each chunk only sees past chunks. This allows the entire model to be reformulated as a chunkwise RNN. Result: constant memory usage, no matter how long the video. Training is two-stage. 1. Attention distillation. A pre-trained one-to-one model teacher guides a lightweight rehire student. Only kernel features are trained, 160 GPU hours. 2. Lightweight fine-tuning. 1,000 iterations on 350K videos, recovers motion smoothness. The result: near SOTA quality, 83.4 on VBench versus 1-to-1's 83.1, with linear scaling. Human studies. Over 40% preferred rehire for consistency and motion quality. On a Snapdragon 8 Gen 4. It generates 10-second videos with 384 ms latency, while flash attention runs out of memory at just 121 frames. And memory: 11x less than flash attention. This isn't just a model. It's a recipe to convert any bidirectional softmax video model into an efficient, on-device system. Rehire, the future of real-time accessible video generation. This week we've seen AI not just get smarter, but rethink its foundations. From InfiniDepth, which treats depth as a continuous function, not a grid, to EAFT, which respects a model's internal knowledge, not just labels. From Transcribe Diarize, which understands conversations as they unfold, to GDPO, which fixes the hidden flaw in multi-objective RL, and Rehire, which brings long-form video to your phone. The thread: efficiency without sacrifice, precision without fragility, scalability without compromise. AI isn't just getting more powerful, it's becoming more responsible, more robust, more human-aligned. So if you're building the next generation of AI, whether in vision, language, or video, pay attention to these shifts. They're not just papers. They're blueprints for the future. If you found this deep dive valuable, hit like, subscribe, and join our community of AI explorers. Drop a comment below which of these 5 papers excites you most. And until next week, stay curious, stay critical, and keep collapsing the future.